And the frame relay devices generally fall into two general categories, and those are DTE and DCE devices. A DTE device is a data terminal equipment. In our case, that's going to be a router. If you look into like other protocols like ISDN, there's a number of devices that can be DTEs, and it even says down here that examples are terminals, personal computers, routers, and bridges. In our case, just think of the router. It's going to be basically where our network ends and the carrier's frame relay network begins. And that said, a DCE is data circuit terminating equipment, and whoops, I didn't put the asterisk in there. Let me pop that sucker in there real quick. Haha, editing on the fly. Anyways, it's also referred to as data communications equipment and data carrier equipment. I've heard data carrier equipment quite often. Technically, it's data circuit terminating equipment, and that's going to be, in our case, the frame relay switch, and specifically the frame relay switch that sits on the outside of the cloud that we connect to. And we'll see some diagrams in just a second that brings us a little bit more into focus. They're generally owned by the carrier, not 100% of the time, but generally. And its main purpose is to provide clocking and then actually an entry point into the frame relay cloud. And that's how I generally differentiate each of these acronyms. I suppose they're not acronyms, they're abbreviations. The C I just think of as clocking, and the T I think of termination, even though you don't want to get mixed up as data circuit terminating. This is your device, and then the DCE device is going to basically be that of the carriers. And like I said, the big thing that it does is it provides clocking to the DTE device. Hopefully associating clocking with the C helps you out to remember which is which. We have a couple diagrams here that hopefully bring some of these concepts into better focus. Here's a simple frame relay network, and this is something we're going to see over and over again when we get into the lab portion. And you can see here the routers are all DTE devices. These boxes here represent frame relay switches, and those are all DCE devices, so they're providing clocking to each of these devices, the DTEs. This is referred to as a frame relay cloud. Basically what that concept means is that you don't care what's in the cloud. You don't care about the path through the cloud. You don't care about what devices are in there, how many devices. Well, you can start to care about how many devices depending on latency. But anyways, you're going to purchase a virtual circuit. We'll take a look at the term virtual circuit in just a bit here. So you're going to say connect R3 to the frame relay cloud, and basically all you're going to see is a connection from R3 back to R1 or to R2 if you so desire. In this case, we just have connections from R1 to R2 and R3. And this frame relay cloud, like I said, that can be 2 frame relay switches, highly unlikely. It can be a billion frame relay switches, equally unlikely. It can be a single carrier. It might be at some point, if this is in Afghanistan and this is in Zimbabwe, this cloud might include multiple carriers frame relay cloud. So it might be that it goes to Afghanistan telco, I have no idea what that would be, out to India telco, to another telco, to another telco, till it gets to Zimbabwe. So you're going through multiple frame relay clouds to get back to R1. The concept of the cloud is basically that you don't know what's in there, you don't care. All you know is you're connecting to one point of the cloud, and then your traffic's going to exit another point of that cloud. And just a quick aside, the concept of the cloud is not specific to frame relay. You can have an MPLS cloud, an ATM cloud, etc. So kind of hammering home the frame relay cloud concept. Here's what you're seeing. You're seeing R1 connecting to a frame relay switch, which is going to be carrier controlled, and then you're seeing R2 doing the same. So when you're sending traffic from R1 to R2, basically what you're thinking is happening is that R1 connects to this frame relay switch, that frame relay switch is directly connected to this frame relay switch, and then it's connected to R2. That's the logical progression of the data transfer. What's actually happening most likely on a physical level is that you have a frame relay cloud with a grip of frame relay switches in there. So you're connecting to this one, and the path through here, it might go from here to here to here to here to here, blah blah blah. It doesn't matter. We don't care about how many switches there are or what the path is through that cloud. That's provisioned by the carrier. This is what we're seeing basically. So this is kind of looking at the statistical multiplexing. A multiplexer or a MUX is something that combines basically smaller, well, it can do it in either way. It could take smaller virtual circuits, channels basically is what they're called, and it can mux them, which usually means to take a number of smaller channels and make it into a big one, or it can go the other way where it takes one big channel and splits it up into smaller channels. In this case, we're looking at a DS1 or T1, as they're often referred to in North America. The T1 runs at 1.544 megabits per second, and if you do the math on that, divide that by 24, you end up with these 64K channels. So T1 consists of 24 64K channels, and that could be multiplexed in either direction. And how that comes into our frame relay is that most of the time carriers are going to sell you a virtual circuit, and again we will be looking at virtual circuits rather quickly here, that come in steps of 64K. So you might order a 128K circuit or a 512K circuit. And remember, with statistical multiplexing, technically each of these could be owned by a separate customer. It could be a virtual circuit going to 24 different customers. And with our example, if this first guy is sending data but none of these other guys are, technically he can burst above his committed information rate, which is his guaranteed rate of 64K, up to the full bandwidth of the DS1 or T1 to 1.544 megabits. Again, we'll go through this in excruciating detail during frame relay traffic shaping and quality of service lessons. Alright, and as promised, we'll now take a look at frame relay virtual circuits. Frame relay virtual circuits are a logical connection between two DTE devices, and in our case that's going to be routers, across a frame relay packet switch network, or PSN. That's the frame relay cloud. I think they refer to it as frame relay cloud far more often than they would a PSN. So just stopping back a bit, your virtual circuit, you would see it as this connection from R1 to R2. You connect to the frame relay cloud or PSN if you prefer that, and then it comes out the other side at this frame relay switch and connects to R2. What the virtual circuit aspect of that is, and we kind of touched on this a little bit with the composition of the cloud being invisible to the customer, is that that circuit actually goes to this frame relay switch, and then let's just say it takes the path of least resistance, goes to this one, 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 and finally comes out this frame relay switch. It could go that way, it could go up this way, it could take any path through the frame relay cloud. That's what we're referring to as the virtual connection. But the virtual circuit to us is just the connection from R1 to R2. This is our VC here. And then virtual circuits provide a bidirectional communication path from one DTE device router to another, and they're uniquely identified by a data link connection identifier, or DLCI. You'll see DLCI. Almost everybody I know that I've ever heard say this pronounces it DLCI rather than sounding out each letter of the abbreviation. And the number of virtual circuits can be multiplexed into a single physical circuit for transmission across the network. The network in this case is going to be the frame relay cloud. We kind of saw that with that last slide where you could have technically 24 different customers, each with a 64K channel, in this case a 64K virtual circuit, connecting to a bigger pipe, which would be the T1 or DS1, and then those connect to bigger pipes in the backbone, you know, DS3s, blah blah blah, on and on. This capability often can reduce equipment and network complexity required to connect multiple DTE devices. We'll see this in action when we take a look at frame relay topology, specifically the hub and spoke topologies. I'm not going to go into a whole lot of detail here about why this is, but when you take a look at the hub and spoke, you can see where this does reduce the amount of equipment that you would need to connect multiple DTE devices. And a virtual circuit can pass through any number of intermediate DCE devices or frame relay switches located within the frame relay PSN, or as we refer to it, the frame relay cloud, and we saw an example of that just a second ago. So now these frame relay circuits fall into two categories. They are the switched virtual circuits, or SVCs, and the permanent virtual circuits, or the PVCs. And we'll start looking at these virtual circuits with the switched virtual circuit, or the SVC. You're highly unlikely to ever run across an SVC in the wild, but it's good to learn about them so that you can understand the differences between a switched virtual circuit and a PVC. I've been working with frame relay for a long time, and I don't think I've ever come across an SVC. We did have a bandwidth on demand contract with AT&T that might have used that, but I don't remember. Anyways, I'm digressing. SVCs are basically temporary connections used when you're only going to be sending sporadic data transfers between two routers. I'm going to stop saying DTE devices because we're talking about routers across a frame relay network. And there's 4 operational states. If you studied or used ISDN, you'll be familiar with these 4 operational states. So there's call setup, there's data transfer, there's idle, and there's call termination. So call setup is exactly what it says. It's going to establish the connection between the two routers. And basically there's going to be a lot of magic in the middle here, because you got to think you've got R1 here and R2 over here, and then you could have a ton of frame relay switches in the cloud that connect these. So it's going to say, R1's going to say, I'm ready to send some data. Okay, and it goes to the frame relay switch. Oh, he's sending data. Let's go ahead and create a virtual connection to R2. So you can see there's got to be a lot of protocols and stuff that are going to be in action in the cloud to make this happen. The data transfer is self-evident. It's the transfer of data. And then idle is basically going to be the time when, you know, the circuit is still pegged up, but there's no data going across it. So it's going to be a timer basically that counts down. Let's say it's 30 seconds. So the SVC has been established. You send data. You're done sending your data. 30 seconds later, the SVC is going to go ahead and hit the 4th stage, which is call termination, because there's been no data sent in that window. And then call termination again is pretty self-evident. It's when it tears down the SBC